Just a quick note, whenever you have a pair of electrons like this, that's called a single bond. And we can write a single bond also is just by putting a line like this. So in our NH3 Lewis structure here, we can replace the bonds, these are the pairs of electrons between two atoms, with single lines. And that'll mean the same thing. It's the same Lewis structure, just a different representation. We'll start with the Lewis structure for OF2. First, we find the valence electrons. So oxygen is in group 16, sometimes called 6A. It has 6 valence electrons plus fluorine, which has 7. But we have the 2 fluorines, so we'll multiply that by 2. And that gives us 6 plus 14, a total of 20 valence electrons. Next, we'll put the least electronegative atom in the center of the Lewis structure. That's going to be our oxygen, and then on either side, let's put the fluorine atoms. We'll place a pair of electrons between the fluorine and the oxygen here to form a chemical bond, and then over here. Once we've done that, we'll complete the octets around the fluorine atom. So we'll want to have 8 valence electrons around each fluorine atom. So now the fluorines have 8 valence electrons. They have an octet. We've used 16. That means we have 4 more valence electrons. We'll move back now to that central atom. We'll put 2 valence electrons here, and then 2 here. And we've used all 20 valence electrons, and each of the atoms in this Lewis structure has an octet. So we're done with the Lewis structure for OF2. For the CH4 Lewis structure, let's find the number of valence electrons. Carbon is in group 14, sometimes called 4A. It has 4 valence electrons. Hydrogen has 1 valence electron, but we have these 4 hydrogens, so let's multiply this by 4. If we add that up, 4 plus 4 equals 8. So we have 8 valence electrons for the CH4 Lewis structure. We'll put the carbon in the center. Hydrogen atoms always go on the outside. So we'll put the carbon in the center, and then we'll put the 4 hydrogen atoms around it. Next, we'll put a pair of electrons between each of the atoms to form a chemical bond. So we'll put 2 here. At this point, the carbon has an octet. We've used 2, 4, 6, 8. We've used all our valence electrons, and the hydrogens, they each have 2. This is an important rule. Hydrogens only need 2 valence electrons to have a full outer shell. So the carbon has an octet, the hydrogens each have 2. We're done with this Lewis structure. H2 is probably about the simplest Lewis structure we can draw. So if we count the valence electrons up, hydrogen is in group 1. It has 1 valence electron, but we have the 2 hydrogens. We multiply those together. 1 times 2 is 2. So we have a total of 2 valence electrons. So we'll put our 2 hydrogen atoms right here next to each other, and then we're going to move 2 valence electrons between them to form a chemical bond. And when we do that, we've used both of the valence electrons. Hydrogen has 2. We said that hydrogen is an exception. It only needs 2. And that's the Lewis structure for H2, hydrogen gas. CO2, carbon dioxide, is a little bit more of a complicated Lewis structure, but it's not too bad. Let's count the valence electrons. We have 4 for carbon. Oxygen has 6, but we have these 2 oxygens. And that gives us a total of 4 plus 12, 16 valence electron. We'll put the least electronegative atom in the center of the Lewis structure, that's the carbon, and then we'll put an oxygen on either side. Next, we'll move electrons to the center to form the chemical bonds. Once we form those chemical bonds, we'll complete the octet around the oxygen atoms. We have a total of 16 valence electrons. And now we've completed the octets on the oxygen atoms. But we've used 16 valence electrons, and we don't have any more. The carbon in the center, though, it only has 4 valence electrons around it. It doesn't have an octet. To solve this problem, we can move valence electrons from the oxygen atom to the center between the carbon and the oxygen so that they share valence electrons. So when we do that, the oxygen atom, it still has 8 valence electrons, but now the carbon atom has 6. We're almost there. Let's take 2 from this oxygen, move them to the center. Now, this oxygen here still has 8. This oxygen has 8. And the carbon in the center has 8 valence electrons. And we're using all 16 of the valence electrons here, no more. So this is the Lewis structure for CO2. We call this a double bond. For the BH3 Lewis structure, boron has 3 valence electrons. It's in group 13, sometimes called 3A. Hydrogen has 1, and we have 3 hydrogens. So we have 3 plus 3, total of 6 valence electrons for the BH3 Lewis structure. Since hydrogen always goes on the outside, we'll put the boron in the center, and then we'll put the 3 hydrogens around it. We'll start by putting pairs of electrons between atoms to form chemical bonds. We've created the chemical bonds, but we've used 2, 4, 6 valence electrons, and we only have 6 valence electrons. So how do we complete the octet for the BH3 Lewis structure? It turns out that with Lewis structure there are quite a few exceptions. The octet rule is a very general rule. It works a lot of the time, but not all the time. So for boron, it's one of the exceptions. Boron only needs 6 valence electrons. We'll see more of these exceptions later on. O3 is also called ozone. We have 6 valence electrons for oxygen, and we have the 3 oxygens for a total of 18 valence electrons for this Lewis structure. We'll write the 3 oxygen atoms and we'll just put them next to each other. So 1, 2, 3. Next we'll put electrons between the oxygen atoms to form the chemical bonds. We've used 2, we have 16 more. Let's complete the octets on the oxygens on the outside. So we've used 16 valence electrons. We have 2 more, and we'll put those on the central oxygen. And we have octets on the outside, on the oxygens on the outside, but that central oxygen, it only has 6 valence electrons. So much like we did with carbon dioxide, we can move a pair of electrons to the center. When we do that, these 2 oxygens are sharing those electrons. So this oxygen has 8, the central oxygen has 8, and then this oxygen over here on the left also has 8. When we have Lewis structures like this, there's another way we could draw it. You can see the only difference here is we have the double bond here, and on this one we have the double bond on this side. These are called resonance structures. Often when we draw Lewis structures, you're asked to draw the resonance structures. Those are the different ways you can draw the Lewis structure. Here we have a double bond on the right, and here we have it on the left. We have something a bit odd with this Lewis structure, and that's that plus sign up there. Whenever you have a plus sign, it means the ion, the compound, it's positive. And to be positive, it lost an electron. So when we write up the number of valence electrons, nitrogen has 5 plus the 4 oxygens. We need to subtract 1 valence electron because the plus means we've lost 1. If this were a negative sign, it would mean we gained 1. So 5 plus 4 is 9, minus 1. We have a total of 8 valence electrons for this NH4 plus ion. We'll put the N in the center, hydrogen, always on the outside, and then we'll put the 4 hydrogens around it. We have a total of 8 valence electrons. Let's put a pair of electrons between each of the atoms, form a chemical bond. There. So we've used all 8 valence electrons. The nitrogen, it has a full outer shell, has an octet, and the hydrogens, they only need 2. They all have full outer shells. That's the Lewis structure for NH4+. It's called the ammonium ion. For SO4 2-, the sulfate ion, sulfur has 6 valence electrons. Oxygen also has 6. We have 4 oxygens. And this 2- up here, that means we have an extra 2 valence electrons. So we'll add those right there. We have 6 plus 24, that's 30, plus 2 gives us 32 valence electrons for this Lewis structure. We'll start by putting the least electronegative atom in the center, that's the sulfur, and then we'll put the 4 oxygens around it. We have 32 valence electrons. We'll put 2 between each of the atoms to form the chemical bonds. Then we'll go around and complete the octets on the oxygen atoms. Whew, that was a lot of electrons. If we add all of these electrons up, you'll see that we've used 32 valence electrons. The sulfur has an octet, as do all of the oxygen atoms. It looks like we're done with this Lewis structure. Everything has octets. We've used all the valence electrons. It's all good, right? However, if you're in a more advanced chemistry class, you'll learn that sulfur and other atoms in the periodic table that are in period 3 or below, they can have what's called an expanded octet. An expanded octet means that the central atom there would have more than 8 valence electrons. The way we tell is we check the formal charges. I'm not going to do that right here, but I'll show you what the correct structure looks like after we find the best formal charges. This is actually the best Lewis structure for the sulfate ion. All of the formal charges are 0. Each of the oxygen atoms has 8 valence electrons. The central sulfur has 2, 4, 6, 8, 10, 12, but that's okay. It can do that because it's in period 3 on the periodic table or below. It can have that expanded octet. So this is the best Lewis structure for SO4 the sulfate ion. We should also put brackets around this with that 2- to show that it's an ion. And there you have it, the Lewis structure for SO4 the sulfate ion. For phosphate, we have 32 valence electrons. It's likely when you do the Lewis structure, you'll come up with something initially that looks like this. And that makes a lot of sense. We've used all 32 valence electrons. Each of the atoms has an octet. Looks like a pretty good Lewis structure. Again, when we have atoms that are in period 3 or below on the periodic table, especially things like sulfur and phosphorus, we should check the formal charges to make sure that this is the best or the most favorable Lewis structure. I won't do that here. There's a link to a fuller video you can watch. But when we do it, here's what we end up with. The only difference is that we have a double bond here between the phosphorus and the oxygen. Everything else stays a single bond. We still use the 32 valence electrons. So checking the formal charges is a very good idea if you're in an advanced chemistry class. One last thing, we should put brackets around this since it is an ion, and then we'll write the 3- right up here. And that's the Lewis structure for PO4 3-, the phosphate ion.